Hello everyone, today we're going to be going through the electrophilic substitution mechanism. So this one is primarily encountered with reactions involving benzene. Before we get into the example that is on the screen, let's recap some of the points around the mechanism. So it is the mechanism that is predominantly seen in benzene reactions. And the reason why is because benzene routinely undergoes substitution reactions over addition reactions, because by doing so it gets to retain the stability of the pi system, the pi delocalized ring. Whereas if it was an addition reaction, the species form would be higher energy than if it underwent substitution. So substitution is favoured to retain the stability of the pi system. The next point is that the electrophile is always generated in the same way. So it's generated when the catalyst reacts with the reagent. Okay, so before benzene can actually react with the reagent, in this case it's this acyl chloride, the electrophile has to be generated. And the way that happens is the catalyst reacts with the reagent to produce the electrophile. So that is often written as an equation first before doing the mechanism. So that is actually what I'm going to start with. So let's get into it. So we have benzene reacting with an acyl chloride. This one is ethanol chloride. And you can see that the hydrogen, which I'll just mark in blue here, has been swapped for the acyl chloride molecule, and HCl has been kicked out. So the hydrogen has been substituted for the acyl chloride molecule. And the catalyst is aluminium trichloride, which you will see pretty much the vast majority of the time with these benzene mechanisms. So let's go ahead and show the generation of the electrophile. So what happens is you have AlCl3 reacts with the acyl chloride, and if I just show at the top here the dipoles, so delta minus, delta plus, delta minus. So this bond is easily cleaved because the CCl bond has a dipole, is weakened, and is attracted to the AlCl3 catalyst, which is electron deficient. So it's an easy, favourable reaction. So the chlorine is taken on by the catalyst to produce AlCl4 minus. So it takes the electrons from the covalent bond, plus the electrophile, which is this bit. So what is that? It is CH3CO. So that's what it looks like in an equation. So let's take a look at the mechanism now. So we have the benzene ring, and I'm going to do it using the 3 double bonds notation, which is what you tend to see at university and is accepted at A level, as well as grade 12, as long as you show clearly what you're doing. So one of the double bonds of the benzene attacks the electrophile that's just been made. So the positive charge, by the way, sits on the carbon there, and then that goes to there. Then what happens is the pi system temporarily breaks as a result of the carbonyl bit being added. So now at this point, which I'll just circle in red, that has become saturated. It's a tetrahedral intermediate. And the positive charge, because an electron pair has been used to bond to this electrophile, is now going to sit on this corner. Then remember, before I show the final bit, let's recap the definition of a catalyst. So a catalyst is a species that participates in a reaction but is not used up. So we have to see the catalyst at the end being regenerated. We have to get it back at the end. So this is what happens in the last step. So the AlCl4- that was produced in this equation now takes off this hydrogen. So if I just draw here, so Al, so 1, 2, 3, 4, and the minus sits, you can think of it as being on the outside like that. And one of the AlCl bonds break and the electrons are transferred from the bond to grab the hydrogen. Then the electrons in the CH bond collapse back into the ring to regenerate the benzene ring. So we end up with the benzene ring being regenerated, the C double bond O CH3 plus HCl, and the AlCl4- has now become AlCl3. So we can circle that and say that the catalyst has been regenerated, thus fitting the definition of a species that participates in the reaction but is not consumed. Okay, so I hope that's helpful.